AI Paper Podcasts. Today's paper is Exploratory Memory-Augmented LLM Agent via Hybrid On and Off Policy Optimization, or MPO Squared for short.
Current LLM agents trained with reinforcement learning hit a massive bottleneck. They rely entirely on exploiting pre-trained knowledge rather than actively exploring novel states.
MPO Squared solves this by combining non-parametric memory, storing self-generated tips from past failures, with parametric RL updates that internalize those tips directly into the model's weights.
The framework uses a brilliant hybrid of on-policy and off-policy optimization. It is essentially performing reward-guided knowledge distillation.
The results are staggering. Using Quinn 2.57b Instruct, MPO Squared achieved a 128.6% improvement over GRPO on the ScienceWorld benchmark and 11.3% improvement on WebShop, plus incredible out-of-distribution adaptability.
It completely redefines how we approach the exploration-exploitation trade-off in language agents.
Okay, so that is the tightly packed 1-minute summary. But if you are actively building autonomous agents or engineering the RL pipelines that train them, the real question is how Microsoft Research and KAIST actually pulled off this hybrid architecture. So in this deep dive, our mission is to unpack exactly how MPO Squared works under the hood and, what it means for the future of self-improving models. Let's start with that core bottleneck. Why do standard online RL algorithms just hit a wall when they have to explore?
Yeah, we see this stagnation constantly with algorithms like GRPO, which is Group Relative Policy Optimization. The issue isn't that the model lacks prior knowledge, it's the exploration policy itself. In a standard GRPO setup, the policy generates multiple rollout trajectories for a given task, and then the model weights are updated based on the relative scalar reward of those trajectories.
Right, which sounds fine in theory, But
the fatal flaw for complex multi-step reasoning is that those trajectory rollouts operate in total isolation.
There's literally zero continuity between attempts. Like, if an agent needs to execute a really long 20-step sequence in an environment where rewards are sparse and it fails at step 2, every single rollout in that batch might just return a reward of 0.
Exactly. The algorithm suppresses the probability of those trajectories, sure, but it provides no intrinsic mechanism for the agent to analyze the localized failure point. It lacks the scaffolding to systematically search the state space, so it just defaults back to its pre-trained priors.
It's just guessing in the dark.
Essentially, yeah. If its prior dictates a certain action and that action fails, it will likely sample that exact same failing action in the next rollout because it hasn't gathered any new contextual information to shift its probability distribution.
The paper actually highlights this beautifully with a really specific scenario from the ScienceWorld benchmark. It's the red light bulb example. So the agent gets this seemingly simple task, turn on the red light bulb. It spawns in a starting state labeled the hallway, it observes the environment, and there is no red light bulb present.
Right. But a standard GRPO agent, trapped by its priors, simply outputs the action focus on red light bulb.
Even though it's clearly not in the room.
Even though it's not there. The environment returns a failure state, indicating the object isn't present. But because the agent has no mechanism to carry that specific semantic failure forward into its next exploration strategy, it just loops.
It just sits in the hallway, repeatedly attempting to focus on an object that isn't there until the environment finally terminates the episode.
It is entirely lacking the intrinsic drive to transition to a new state, like, say, navigating to the workshop to actually search for the bulb. That is the exact exploration bottleneck MPO Squared targets, and it attacks it first through non-parametric memory.
Right, the tips. They use a specific prompting mechanism to force the policy to reflect on its failures.
Instead of just terminating a failed rollout, tossing that 0 scalar reward to the RL algorithm, and starting fresh, MPO Squared initiates a reflection phase. The agent takes the final state of the failed trajectory alongside a specific tip generation prompt and synthesizes a localized summary of the failure. And then it stores this summary, the tip, in an external memory buffer.
It's basically writing notes for itself, constructing a localized heuristic for its future iterations. In that ScienceWorld lightbulb task we just talked about, the MPO Squared agent actually generates a tip that reads, "You focused on the red light bulb, but did not complete the task. You are in the hallway and need to find a way." It semantically maps the failure to its current state.
Which is incredibly useful. Now, utilizing external memory to bypass context window limitations or improve zero-shot performance is a well-trodden path. Frameworks like Reflection have demonstrated that appending past failures to the prompt improves immediate success rates.
But the literature consistently shows that the performance of these purely non-parametric methods saturates very quickly.
Because you are ultimately bound by the static parameters of the base model. You're just depending context. The model's internal representation of the task distribution never actually shifts, and eventually the attention mechanism struggles to effectively weight a massive buffer of past tips.
That limitation is the genesis of MPO Squared. The architecture treats the non-parametric memory not as the final solution, but as an intermediate scaffolding. The objective is to leverage the external memory to guide the agent towards successful high-reward trajectories and then mathematically boke that exploratory behavior into the parametric weights.
The model learns to internalize the logic of the tips.
Meaning that at test time, it won't even need to query the memory buffer. It will have shifted its priors to naturally explore. But to understand how they bridge that gap, we really need to break down the heavy machinery of the paper, the rollout and update modes.
Right. The architecture operates in two distinct phases, starting with how the agent interacts with the environment during the rollout phase. At each decision step, the agent samples between two different operational modes. The first is prompting without memory. This is your standard autoregressive action generation. The policy conditions its action solely on the current state observation and the overarching task instruction.
And the second mode is memory-augmented prompting. Here, the agent actually queries its accumulated memory buffer. It uses cosine similarity to retrieve the top 10 most relevant tips based on its current state. It then concatenates those tips into the prompt, conditioning its next action on both the state and the retrieved heuristics.
And the authors empirically determined that a probability parameter of 0.25 for this memory-augmented mode yields the most stable convergence. You really don't want the agent relying on the memory 100% of the time because the base policy still needs to independently attempt actions to generate the contrast required for the RL updates.
That 25% injection of memory just acts as a behavioral perturbation. It pushes the agent out of its local minima. But the true innovation of MPO Squared lies in the update phase. Once a batch of rollouts is collected, the trajectories generated without memory are updated using standard on-policy RL. The trajectories that utilize the memory-augmented mode, however, are routed through a bifurcated update process.
This is where the hybrid nature of the framework really materializes. The first path for these memory-augmented rollouts is an on-policy update. The algorithm updates the model weights using the exact same prompt configuration, including the retrieved tips that it used during the rollout. This reinforces the model's ability to utilize provided context.
But the second path is the off-policy update, and this is the core mathematical driver of the entire paper. In this mode, the model executed its rollout and achieved a high reward by leaning on the retrieved tips. But when the algorithm calculates the log probabilities to actually update the weights, it dynamically strips the tips out of the prompt.
The policy gradient is computed as if the tips were never there. If we trace that mechanically, you have a teacher distribution, which is the model augmented with helpful tips, and a student distribution, which is the base model operating solely on the state observation. By applying the advantage generated by the teacher's trajectory to the student's log probabilities, you are forcing the student to maximize the likelihood of that successful sequence independently.
It is reward-guided knowledge distillation. High-reward exploratory behaviors originally unlocked by the memory buffer get reinforced in the base weights. The model literally absorbs the exploratory logic. But structurally, anyone working with policy gradients knows that off-policy training is highly volatile.
Volatile is honestly an understatement. If you run this naively, the mismatch between the behavior policy, the one that generated the action using tips, and the target policy, the base model without tips, causes catastrophic instability. Your important sampling ratios diverge, your gradient norms explode, and the training just collapses into NaN values almost immediately.
Because if the base model sees a token in the trajectory that was heavily reliant on a specific tip, but that tip is now missing from the prompt, the baseline probability of that token drops to near zero. And in the math of important sampling, dividing by a near zero probability causes the gradient magnitude to shoot to infinity.
Exactly. The model tries to update its weights way too aggressively to account for an action it never would have taken on its own. So to stabilize this, the authors implement a highly effective advantage masking mechanism. They establish a probability threshold, denoted as delta. During the off-policy update, they evaluate the probability of each token under the base policy.
And if that probability falls below delta...
Right, meaning the token is too radically divergent from the base model's current distribution, they simply apply a binary mask to the advantage term, zeroing it out.
It completely suppresses the gradient update for that specific token, preventing the explosion while still allowing the model to learn from the rest of the trajectory. It's a brilliant, localized clipping mechanism. But even with stable off-policy updates, if the environment itself is entirely devoid of extrinsic rewards, the agent might still suffer from entropy collapse.
Which is the final piece of the architectural puzzle. To maintain exploration in severely sparse reward landscapes, MPO Squared integrates an intrinsic reward mechanism. They draw heavy inspiration from random network distillation, or R&D. The agent maintains a historical ledger of distinct states it has visited.
And when it encounters a new state, it calculates the cosine similarity against its history. If the state is sufficiently novel, the framework injects an intrinsic reward bonus directly into the advantage calculation, supplementing whatever extrinsic reward it might get from the environment.
This intrinsic motivation structurally maintains the policy entropy. It ensures the model is mathematically incentivized to push into unseen areas of the state space, which continually feeds the memory buffer with diverse experiences, which in turn feeds the off-policy distillation process. It is a fully closed loop system for self-directed exploration.
The theoretical elegance of combining self-reflection, advantage masking, and intrinsic motivation is compelling, but the empirical results are what really elevate this paper. Let's look at the testing methodology. The researchers utilized Qwen 2.57b Instruct, a highly capable open-source model, and evaluated it on two notoriously complex environments, ScienceWorld and WebShop.
ScienceWorld is particularly brutal for LLM agents. It consists of 19 distinct multi-step elementary science tasks. The state space requires deep exploration, hypothesis testing, and sequential logic. If you want to melt an object, you have to find a heat source, navigate to it, activate it, and place the object correctly.
And WebShop is a fundamentally different domain. It's an HTML-based simulation of an e-commerce platform where the agent has to parse complex DOM structures, search, and navigate to purchase specific items based on granular user instructions.
Both environments severely stress test long-horizon planning.
So let's look at the hard metrics on ScienceWorld. The base Qwen 2.57b Instruct model achieves a score of -61.3. It completely fails to navigate the environment. When trained with standard GRPO, the performance climbs to 33.8. It learns basic state action mappings, but it fails on deep sequences.
The jump with MPO Squared is remarkable. It achieves a score of 75.9. That is a 128.6% relative improvement over the GRPO baseline. Furthermore, on 7 specific tasks within ScienceWorld, tasks involving complex interactions like electricity or specific chemical states, the MPO Squared agent began training with negative rewards and actually converged to a perfect score of 100.
It didn't just improve, it achieved total mastery of tasks that GRPO could not penetrate. And on WebShop, the MPO Squared architecture scored 88.3, representing an 11.3% improvement over GRPO. It also outperformed much more complex specialized baselines, like GGPO, which is designed specifically for generalist policy optimization.
But from an engineering perspective, whenever you introduce external retrieval and generation steps into the training loop, the immediate concern is computational overhead. Generating, embedding, and retrieving text-based tips via cosine similarity at every single decision step introduces non-trivial latency to the rollout phase.
The authors are very transparent about this cost. Their analysis shows that the memory mechanism adds approximately 19% overhead to the rollout time. On their specific hardware setup utilizing 8 A100 GPUs, that equates to roughly 50.4 extra seconds per training iteration compared to standard GRPO.
It is a definitive upfront tax on your compute budget. However, the trade-off heavily favors MPO Squared when evaluated on sample efficiency. Because the hybrid architecture actually learns the structural mechanics of exploration rather than relying on random stochastic wandering, it requires drastically fewer trajectories to identify high-reward states.
So the total wall clock time to reach policy convergence is significantly shorter than the GRPO baseline.
Exactly. You pay a 19% latency tax per step, but your model requires exponentially fewer steps to reach state-of-the-art performance. For teams optimizing their RL pipelines, that reduction in total sample complexity is massive. But honestly, the most significant finding in the paper, the data point that truly validates the architecture, is the out-of-distribution or OOD Generalization experiment.
This is where we see the difference between a model memorizing task-specific heuristics and a model learning a generalized exploration algorithm. The researchers took a policy fully trained with MPO Squared on a biology-specific task within ScienceWorld. They then deployed that exact model into an entirely unseen domain, an electricity task.
And crucially, they froze the parametric weights. They did not apply any further gradient updates in the new environment. They simply deployed the frozen model and allowed its non-parametric memory buffer to accumulate new tips as it interacted with the electricity domain.
It was a zero-shot domain transfer for the weights, but a few-shot domain transfer for the memory buffer.
The adaptation was immediate. Across 3 distinct OOD scenarios, the MPO Squared model demonstrated an average performance improvement of 136% within just 10 interaction steps. The standard GRPO model, subjected to the same transfer, failed to adapt meaningfully, and in several instances, its performance degraded below the baseline model as its rigid priors collapsed in the new state space.
The MPO Squared model didn't just learn the rules of biology. By internalizing those off-policy updates during training, the base weights fundamentally learned how to deploy memory. They learned how to generate useful reflective notes, how to parse those notes when retrieved, and how to systematically search in unknown state space.
It internalized the abstract process of scientific discovery and environment mapping. The model learned how to be an agent.
Which brings us to the core takeaway for the AI researchers and engineers listening. Why is MPO Squared a critical development for agentic workflows? For the last year, the prevailing strategy for improving agent reasoning has relied heavily on human-engineered heuristics, curating massive offline datasets of successful trajectories, or utilizing expensive, closed-source API calls to models like GPT-4 as a crutch to guide smaller models.
This paper demonstrates that those dependencies are not strictly necessary. You can bootstrap complex exploratory reasoning in a 7B parameter open-source model entirely through its own self-reflection. By pairing a dynamically generated external memory buffer with a rigorously stabilized off-policy RL algorithm, the model becomes a self-contained evolutionary system.
It generates its own curriculum of failures and distills those lessons directly into its parameters. It is an incredibly powerful paradigm for compute-optimal scaling.
And it leaves us with a fascinating, highly provocative implication for the future of model training. MPO Squared proves that an LLM can generate its own structural scaffolding, these text-based memory tips, use that scaffolding to achieve a high reward state, and then mathematically internalize the behavior off policy, so the scaffold can be completely discarded.
It absorbs the utility of the external tool.
Exactly. If we scale that principle beyond simple text tips, what happens when we apply this to code execution? Could future models write entirely new, complex software tools in a sandbox during a rollout, execute them to solve an intractable reasoning problem, and then utilize off-policy distillation to absorb the algorithmic function of that tool directly into their own neural weights?
They could effectively consume the tools they built,
permanently expanding their parametric capabilities without ever needing the external tool again.
a self-compiling intelligence. That is a brilliant thought to leave on. Thank you all for joining us on this deep dive into the paper. We will catch you on the next one.